Hello, this is Brandon Wolfe. I'm a data science student at the University of Oklahoma. This is my presentation for the completion of Computer Science 5593. I'm going to be identifying variable stars from the Large Synoptic Survey Telescope. The outline for what's going to come, and I'm hoping to finish this in 15 minutes or less. I'm going to show you the abstracts, introduce you to the data set, give you some references, talk about how I got my results, draw some conclusions, and then show you how the software works. The basic idea is that adaptive optics, which is removing the blur that comes from the atmosphere, has allowed us to put a whole bunch of ground-based telescopes that are going to be superior even to the Hubble Space Telescope. And that means that we're going to be observing millions of stars instead of tens of thousands of stars. And the best way of analyzing those would be with a computer as the first step. The data set comes from a Kaggle competition from the LSST. It has a training and a test set. The training set is representative of the standard sky survey, tens of thousands of stars. The training set, and the test set is 3.5 million objects. So this is such a huge number that we really need machine learning to do what people have done by hand in the past. The Large Synoptic Survey Telescope is getting first light. It's a ground-based telescope that uses really a remarkably large mirror to see more of the night sky that has been able to be seen before. This was built in Tucson, Arizona, where I'm located, underneath the football stadium. It also has a passband exchanger, which is great for doing not spectroscopy, but getting a lead on. They've picked these colors to be able to differentiate, say, different types of supernova. So by looking at the yellow versus the blue bands, you'll be able to tell the difference between two different supernova type stars as a variable star. The LSST passes to you, the data scientist, a whole bunch of raw data. This comes in the different passbands, so this would be the light that was red, the light that was green, and so on. And as you can see, it's just all over the place. We need to do a whole lot of feature engineering in order to turn this into something. It has a couple of challenges. The first is that the data is sparse, especially for the test set, the 3.5 million one. You only get a few data points, and from that you're supposed to construct a period. It seems like it's impossible. And also, it's not simultaneous across filters, so it takes some time for them to switch the yellow out with the red, and during that time, you're not observing them both at the same time. So the very first thing we needed is to find an algorithm that's going to knit all of those observations together in some way. The times between here and here that you weren't observing the star at all, the times between the lights. So yeah. The related work, I'm following this paper here by Deb and Singh. I was attracted to it because they're drawing a map of each star on just two axes, and they're claiming that the principal component analysis, they only need the first component in order to do classification, which would be fantastic. It would be human readable and not just computer readable. But there's been research on this for more than 100 years. So, for example, here are some variable stars from Popular Science in 1906. This is an Algol star. We'll be seeing Algol stars from the LSST database in just a moment. One of the better references that I found that's actually not published was a presentation. This guy appears to be making the data set that I'm going to be using. And he's discussing here what makes the data set just so difficult. So what I've found basically is that the work that I started with was insufficient. They were able to use only one principal component and make everything really nice because they were only looking at a library of periodic stars whose period had already been cataloged. The LSST data has periodic stars, yes, but it also has quasi-periodic, stochastic, transient, and these kinds of situations, finding the period fully automatically is only maybe 10 or 20% accurate, according to the literature. So the approach that I adopted from this paper will work for some parts of the LSST data, but not so well for other parts. The strategy is to characterize each star according to only two axes, the log of the period, characterizing how quickly oscillations happen, and the first principal components, which characterizes the shape of that oscillation. So this axis is going to be the difference between a star going woo 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 and a star going woo 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 woo, and then up and down, once you spread those out, you can take a look and see if they're both going woo, or is one going woo and one's going ee. So up and down tells you the shape of a particular oscillation, one of the oscillations, and left and right tells you how fast they come in. My objective is to put each of the stars in the LSST data onto this map, and then start off as many k-means clusters as there are in the data set at their centers. And then I should just be able to read off what the outliers are as being the stars that are in some sense weird, in the sense that they're outside of their clusters. This is the graph that was produced by Seb and Singh, the map of each one of the stars. Here is the periodic star and where they live on this map. The reason I like it, again, is that it's not just their standard data science, I put the model into a black box and there's no way of interpreting it. I can clearly interpret both of these axes in terms of physical quantities. So this is the log of the period and this is the shape of a pulse. The analysis plan, okay, so that's the end of my result of the past work. The analysis plan requires 4 steps. I'm going to find the period from the raw data, interpolate it onto a vector of size 100, turn that into a matrix upon which I can do principal component analysis and then cluster the results. This step, the period finding, is by far the most difficult step. So you want to start off with the real raw data, and this thing is actually oscillating with some period that you can't tell because maybe the period is shorter than this particular observation, or maybe it's longer and then it's being observed at some other point in its phase over here. So you need to be able to fold the light curve in such a way as that all of these red dots line up into a perfect line, and they do. The reason why it's one of the most thorny optimization questions I've ever seen is because the optimization function has such an unbelievably steep gradient, and it also has both global and local minimum. So this was a brute force approach. I just only enforcing that there is a period, in other words, the function is periodic. How close can you get the line to each one of your observations, characterized by the root mean squared? There's a minimum here, but it's very difficult to find. You have to have a huge number of function evaluations in order to be able to find it using brute force. Also, using any kind of an algorithm, the gradient here is terrible. So anything in what's called the NL opt library was not able to find a global minimum. The heuristic I wound up using was simulated annealing or a particle swarm. They both have about the same results, but both of them, because they are random, don't always lead to the correct result. So I would like to have the correct result all of the time. It winds up that I can only do that over a particular domain. So this is an issue. The period goes between, the log of the period goes from -1 all the way up to 3. So I would like my search to be able to execute on that entire domain. I cannot, and it finds the period of this kind of a function over that huge of a domain. I need to restrict my domain in order for the execution of the time to be anything less than 1,000,000 years. So that means that I need to use some kind of domain knowledge in order to say, okay, I'm going to search in this domain, and if I find the correct period, then I know it's one of these stars, and so on. So I cannot fully automize I can automate it, but it's going to require domain knowledge in order to restrict the area over which you're searching for the period on this thing. So this is just a quick illustration of how bad this gets. The reference is down here. I would like to find the line that gets as close to these points as possible. And there's a couple of competing points here and here. If I put in more function evaluations, they look like this, here and here. Now this one looks a lot better. But they're really periodic. Finding the global minimum for this thing is going to be absolutely horrendous. And it gets even worse because if you put more function evaluations in and zoom in, then you find that even this little end of it is itself periodic, and you're trying to find the difference between two local minimum of this periodic thing at the end of this periodic thing at the end of that thing. It's a really thorny optimization problem. So I knew it was possible because I was able to find a couple of good light curves. This one looks like it's a chaotic. That's the difficulty, is I don't know a priori if this is periodic, it's going to make a nice line, or is it in fact going to stay like this because it's an active galactic nuclei? So the answer to this quandary was to apply domain knowledge and go through each of the classes in the training set and figure out what the restricted range of the domain should be. So binaries are on the order, eclipsing binaries are on the order of 1 day. Algols are on the order of 0.1 days, light arrays are same, and then you search for the periods within the known domains. And restarted my analysis with this in mind, and I'm only going to be looking at types 92 and 16. And look for now, and looking for periods on the order of 0.1 days. So it improved from the poor centering before into the better centering now, and I have at that point found the period that folds the light curve and centered it in the middle. That gives me a bunch of information. It gives me the amplitude, the period, and the shape of the pulse for classification. So an awful lot of feature engineering went in there. The second step was interpolation. There's a couple of possibilities. So the problem is that different stars will be observed a different number of times, and if I'm going to do PCA, I need the vectors to be of the same length. So the green dots represents interpolation between the data points. First time I tried that was what's called a Loess function. It did an okay job, especially for the nice smooth possibilities, but not so great in other chances and other situations. So the second time I tried it out, I used smooth splines. This is 9 stars of type 92. This is 9 stars of that algol type that I was talking about before. A nice sharp loss of light. Okay, and using these 18 stars, I was able to make a matrix, an 18 by 100 matrix upon which to run PCA. The clearest explanation I've ever heard for principal component analysis is that you break up something like, for here, a handwriting sample, number 2, into a whole series of vectors which represent parts of all of the different kinds of numbers, and then you can make the number 2 out of a certain amount of this, and a certain amount of that, and a certain amount of this. So if you use only the first 5 of these, then you can reconstruct the number 2 as this fuzzy thing. And then the next 25 a slightly less fuzzy thing, and then 100 principal components will really reconstruct your function. The faces in this case, so the numbers that you're trying to identify, are the light curves. Can you distinguish between each one of these using only the principal component? Yeah. This is a scree plot, and most of the variance is contained in the first component, although there is quite a bit that's left afterwards. Here's vividly what it looks like. This is the reconstruction after only one principal component for the first 5 of the light curves that I showed earlier. Here are the first 5 reconstructed only the first principal component for the algol stars. Alright, so we've run principal component now and are ready to map. My first try at this, using the simulated annealing and the Loess interpolation, wound up with this vertical line here for stuff that was not periodic. I was able to observe that there was some type 16 stars clustered here and some type 92 stars clustered over here. The 92s are really pretty spread out. I should be able to get the type 90 as well. The second try around, using the particle swarm on a reduced domain and smooth splines, my map looks a lot better. I've got a clear cluster of 92s here and a clear cluster of 16s down here. And I can just add in the rest of the stars as I go. So the next step was to cluster it using the algorithm that we wrote in class. Here it is in detail. And doing so, I find 2 centers. There's a center here and a center here. So I'm going to call that a success. I have found the regions of my star map where I would be likely to find a particular star. So type 16 lives on this part of the map with a relatively shorter period, and then type 92 lives in this part of the map. In conclusion, the period was very difficult and needs probably some outside domain knowledge in order to classify. The fully automated classification was infeasible. That means going between all the way to the left and all the way to the right, finding the period of that horrible function wound up being impossible. So that meant that you need to use domain knowledge to limit the period search. So start your algorithm with a test star. Run the period between, say, 0.1 of a day and 1 full day, and decide whether it's one of the types of stars that's in that domain, and then go from there. A lot of the data is not periodic. A lot of it is quasi-periodic. So just if you find something that you know, put it into that category, and then use some of the other classification techniques to go from there. So there needs to be an indicator of the probability of being periodic. This analysis allows you to have that indicator. Also, once you have the light curve that's folded, then you can figure out the percent of each one of the colors. That can be a new feature for each one of the stars. I would like to find a better interpolation function than the two that I've got. The problem is that I need the interpolation to keep really sharp data like this one. This is meaningful data, but then lose the spikiness in through here. So quite a bit of work that can still be done in the period, a little bit of work that can be done in the interpolation. The strategy of using the principal components appears to work terrific. So you can in fact characterize an awful lot about what makes this type of star all the same, because they have a very similar first principal component. So that worked terrific, and the first principal component, this mapping, does tell you, I believe, the most possible out of any of the variables, and then you can go from there, especially if a star is not periodic. So I wanted to demonstrate the software application really quickly, and let me build this thing up. So this was built in Shiny, which is an extension, a library for R. And this is made to give you an intuition of where a particular star is going to fall, and if it can be an overlap, and why, if it might be an outlier, and why. So this guy is in type 92, but you can see why the computer would be confused. It has this dip feature in Comet with the algals. So there's a point at which a big peak looks an awful lot like a large dip, and this is it. Observation number 2, this is pretty clearly a type 92 star. The type 16s come later. So he's right square in the middle, so you can characterize stars that are like this. They go along and they have a long exponential decay, and then a big spike back up to the top, and then another long exponential decay, and that's a periodic thing. You can see that again here. So big spike, not quite as steep as before, and then long exponential decay down to here. Big spike, long exponential decay. Same thing here. So the purpose of this, each one of these three, the other thing to look at is where they're living here. They're right in the middle of their cluster. And so these guys are really characteristic of their type. I'm not really sure about this first one. He's not looking like the same type as everybody else, but he got cataloged that way. This guy is, again, he's overlapped in with the type 16 stars, and you can see why. It's because he didn't quite follow the big spike and exponential decay pattern that the other ones did. Who knows? You know, the people that identify the type of this star, you know, maybe they were wrong. Maybe that needs to be reclassified. It was probably a software thing that classified it in the first place. You can see here, this is our outlier. So this guy does not live in either one of the boundaries, and you can see that he should not. There's a particular point down here that makes him look like he's an algol star that's going to dip down here, but it's only the one point. It's large in magnitude, and so this should be enough. But you can definitely see why this guy would be an outlier. He is identified as an outlier using the k-mean strategy, and so he would be removed and placed into the outlier category if I was doing the classification. So great success. I was unhappy when that showed up, but that was the outlier I was looking for. These guys might be algal stars. They might be eclipsing binaries. I'm not entirely sure, but you can see in the graph that it has a different appearance to these guys that were big spike and then exponential decay. This guy is the first of the algal stars that has a downward spike. And he lives right in the middle of his cluster with the other algal stars. This you can see where I would not be happy with the interpolation function. It's done a lot of smoothing, and I'm not getting these features down here, but he still lives right in the middle of his cluster. So it's acceptable to smooth out a lot of that information. This guy, another outlier, he's weird, and he does look different than the rest of these. Really clearly defines pulse that doesn't come out of nowhere. There's kind of a slope here and then a downward pulse, so he's weird. He doesn't fit into his class all that well. A little bit better into his class. Huge spike here. And that's it. Okay, so in final conclusion, I managed to, I wanted to, all the way up at the beginning here, I wanted to build a map. And on that map, I wanted to place stars on the log of their period and their first principal component. I wanted to be able to identify outliers as being outside the boundaries of the clusters around identified types of stars. And that is precisely what my application demonstrates, that I've got two clusters here for two types of stars, and I've got an outlier that can be removed from the data set using this technique. Thank you.